So, excuse me, we're done talking about particle statics, and now we're going to talk about, really in some way or another, the topic for the rest of the class, which is statics of rigid bodies. So, new topic, rigid body statics. Yeah. And so when we're talking about rigid bodies, the change from particles to rigid bodies is that now objects have length dimensions. And there are two consequences. The first one is that now we care about objects' orientations. If there's a finite distance between point A and point B, then where those lie relative to each other tells you the object's orientation. So the orientation of the rigid body matters now. And because of that, the location where the forces are applied matters now. Let me say the location where loads are applied. That's more general because that includes couples that we'll talk about later. But locations where the loads are applied matters. For example, say these are two top views of cars. And draw it again. I don't have to. Whoa. Oh, I spoke too soon. Okay, and say that, so these are cars on ice. The ice is so there's no friction or low friction. And let's say 50,000 Newton forces are applied to each of these cars. On this one, it's applied here. And on this one, it's applied here. Well, thinking of this as a particle, the resulting motion is exactly the same. Newton's second law says add up all the external forces. That's equal to the mass times the acceleration of the center of mass. But you know intuitively that the motions are going to be different. If you apply that 50,000 Newton force through the center of mass of the car is not going to rotate at all. If you apply this 50,000 Newton force to the end, that car is going to spin around. Okay, and so if you're thinking of these as particles, that's the same thing. Thinking of these as rigid bodies, those are two different things. And so that's what we're introducing now.
Question.
Yep.
Wouldn't the car with the force applied to the one end only spin including 5 friction or other like air resistance?
No, it would. They would both. The center of mass of both of them would accelerate at 50,000 divided by the mass of the car. But this one would spin around end over end. It would get an angular acceleration from that force. Okay, so in order to talk about these orientation changes, we have to introduce this new quantity. So there's a new definition that we need for rigid bodies. And that is the moment. People tend to just call it the moment, but this is the moment applied by a force. So the moment of a force about a point. And you can't define a moment until you've specified what force is applying that moment, until you've specified the point that I'm going to call the about point. And the definition is like this. So imagine this is your rigid body, just some arbitrary thing. And we'll say that this is the about point A. And there's a force F applied to the body at this point P. So this is the force vector F. Then define a new vector that goes from the point A to the point P. So A is what we're going to call the about point. P is where the force is applied. And that row vector is a vector from A to P. And another way of saying that is, in other words, the row vector is equal to the coordinates of P minus the coordinates of A. So if you define all these vectors this way, then the moment produced by this force F about the point A, I'm going to write as m sub A, and in general that's going to be a vector, and that's equal to the row vector crossed with the force vector. To make intuitive sense out of that, think of a bolt, like a stuck bolt that you're trying to turn. With a wrench. And if you're trying to turn this bolt, think about applying a force here versus applying a force here. Even though these forces are both the same, you're talking about applying this force F at just two different spots. Applying it all the way at the end of the wrench is going to give you a better chance of turning that bolt than applying it halfway down. And if you applied this force here, then no matter what force you applied, that bolt isn't going to turn. In fact, if you applied a big enough force, that bolt's just going to strip right out, just rip right off of the rest of the bolt. But it's never going to turn because of this mathematical relationship between the moment that causes the rotation and this vector that goes from the about point. In this case, the about point would be there, and the force, the point where the force is applied, which would be here, here, or here. Okay. The moment is always a vector. Its magnitude you can think of the sort of the second definition of cross product that I gave a while ago. The magnitude of the moment is the magnitude of the force vector times the magnitude of the row vector times the sine of the angle between them. Okay, so first of all, just thinking about the magnitude, when are you going to get, so say that rho is 50 newtons and say rho is 0.5 meters and F has a magnitude of 50 newtons. When are you going to get the biggest magnitude for the moment? Like, what's the angle that's going to give you the biggest magnitude for that moment? So yeah, when those two are 90 degrees apart, you're always going to get the biggest value of that moment. And when those two are parallel to each other, you're not going to get any moment at all. Yep.
The theta is between rho and F, correct?
Yes, that's right. Yep, so theta is the angle between rho and F. And now as for the direction is along the axis of produced rotation you can sort of picture this body being fixed at the about point and just rotating around the about point. So assume that it's fixed to rotate around that point A. And so this is kind of small. I can pass this around, but let me draw a picture of it, and then maybe I can help illustrate with this. So let's say that what we have here is a rigid body and so this piece that's two rods connected, if I apply the right moment, I can get it to rotate this way. Okay. See, can you see in the back what this thing's doing? That's the only way that it can rotate. And the axis of rotation during that rotation is the rod that connects through those two joints. Can you see that? It's rotating around an axis that goes through this rod. So like this is the axis of rotation, or this. It can go either direction. Any questions about what that axis of rotation is, or how you figure it out? That's gonna be sort of a big topic. So the axis of rotation is this way, one of those two. But if the moment is a vector, we need to pick one of those or the other. Okay? There's no such thing as a vector that has two directions. And so how do you distinguish between this way or this way? The right-hand rule. So the direction is along the axis of rotation in the direction following the right-hand rule. Okay, so if a body rotates from so let's say that we have a rigid body that rotates from here to here. That rotation looks like this, the rotation that's produced by that moment. And the right-hand rule, you wrap your fingers in the direction of that rotation, and your thumb This is really the worst drawing I've ever done. Yeah. Okay.
Better than I could have done.
Okay, so if it's rotating, if the moment's making it rotate this way, then your fingers curl with that rotation. Your thumb points out of the page, and so the direction of the moment is out of the page. Yep.
Where would the vector F be in this case?
So what you're thinking about is what rotation that force F would
I mean
produce.
in the previous example.
Yeah, so if it's like in this, let me do this example first.
Okay.
So like in this example, we know that there's a force that if there were no other forces acting on it, it would make it rotate this way. So it could be a force pointing like that, or it could be over here pointing like that. Anything that would make it rotate counterclockwise in that picture. In this example, that force could be it could be applied straight down there, and if that was the case, then this would be rotating like towards us down the front.
Okay.
You know, and so your fingers would curl in that direction, and the moment direction would be that way.
Okay.
Confused as to why it's so if you're taking the cross product of rho, which would be from the point of application
So in this case, should you want me to draw them on here? And
Oh, you know what? I got. Okay. I'm
Okay.
just looking at it backwards.
yeah, so in this case, this would be F. Row would be like from here to here. And you have to put them tail to tail. That's a key thing.
Yeah, I had my A and my P mixed up.
Okay, yeah.
Row going in.
And so then the moment is this way. But so you take this force, put it tail to tail with this row vector. In this case, these two, the way I've drawn them, are perpendicular. That doesn't always have to be the case. And then the moment is perpendicular to both of them like this, because that's required by the cross product. Any other questions? And we're not going to use this intuitive idea for calculations, but it's always useful to keep that in mind as a way to sanity check things. If you think about moments in this way, you can always come back after you do your calculation and check to see whether the direction makes sense. If you forget about this, you don't have any check on your calculations. So it's a good habit to get into. And I'm going to introduce this way to organize moment calculations. So it's actually a way to keep track of all the force and moment calculations. And I call it the Pancake Table. Because of the acronym I use, which is stupid. But I'm not changing it now, because I've been using it this way for 6 years or whatever. Okay, so the table looks like this. Well, the acronym is Pancake, Artists, Row, for Marzipan. Marzipan is like a fancy kind of frosting. It's sort of like halfway between frosting and candy. It's not actually very well suited to pancakes, but you can imagine that there's this like fancy like fresh French pancake chef who like uses this fancy stuff, and he like lives on an island and he has to row his boat to the artisanal marzipan. Okay, that's the idea. And so this leads to this table like this, where the columns are P vector, that's pancake, A vector, that's artists, Greek letter rho, rho, force vector, F, and then M sub A for the moment. And so this P is the coordinates of the point where the force is applied. A is the coordinates of the about point. row you can think of two ways. If you have coordinates for both of these, you can just subtract them. So row is equal to P minus A. But sometimes it saves time not to go through calculating all of those coordinates. So the second way is just to think of row as being a vector from A to P. So row is a vector from A to P. F is the force vector. And then MA is just row cross F. And when we go to the moment equation, the rotational version of Newton's second law, we're going to fill out one row for every force that we have, for every load that we have. And at the end, we're going to have a column of force values and a column of moment values. We're going to add up all the forces, set those equal to 0. That's Newton's second law. And add up all the moments, set those equal to 0. And that's the moment equation, the rotational equation. Any questions right now before I do any calculations about the idea of that table? Yes. So about Newton's laws. Yeah, I'll say that more clearly. But the idea is for every load on the body you're isolating, you're going to have a row. And so at the end, you'll have, say, five rows of things. And you're going to take all of the F values, all 5 of the force values, add those up and set those equal to 0 for Newton's second law. And you're going to add up the 5 values of MA and set those equal to 0, and that's going to be the rotational equation. So it's just a way to organize everything you need for Newton's laws. These two are optional. If you use this second way of thinking about the row vector, then you can skip this step. So I'm going to do a lot of these tables where I just write out row F, MA. Okay? But you always can write the whole thing out, calculate those coordinates. But that'll make more sense as I do problems and stuff. Okay, so let me do an example. Let's say we have this thin plate. And it's connected to the wall by like a hinge or a pin joint. You know, so it can rotate about this axis. And then at the middle of the plate, there's a little hook. And that hook connects to a cable that attaches to the wall. And let's make this, I want this to connect to the wall right above the edge. So this distance here is 1 meter. The length is 2 meters. And the width in this other dimension is 2 meters. I'm going to use a coordinate system that's oriented like this. So this is the x-axis, the y-axis is up, and the z-axis is this way. The z-axis is parallel to these two edges. And let's define, we're going to choose our about point to be here. So if we know that the tension in that cable is something, looks like 10,000. So if the cable tension is 10,000 newtons, what's the moment produced by the cable on the plate? So we're isolating that plate about that point A. Anybody have any questions about the idea, the setup of the problem? So we're trying to figure out, we're isolating that plate, and that cable is applying a force to the plate, and we're trying to figure out what the moment is that cable applies to the plate with the about point chosen over there arbitrarily. Yep.
Are you assuming the hook is in the center of the plate?
Yes,
Okay.
that's right. Okay, so let's set up this table. So pancake, artists, row, 4, marzipan. Thanks. Okay, well, in this green coordinate system, what are the coordinates of the point P where the force is applied? And actually, you know what? Yeah, we'll skip a free body diagram for now since we're only dealing with that one force. So, yeah, right. The cable is applying a force to the plate at the origin, right? It's applying the force to the plate at the hook. Okay? Everyone see that? So P is 0, 0, 0. Now, what are the coordinates in this green coordinate system of the point A? You have to go 1 meter in the positive x direction to get here, and then you have to go 1 meter in the negative z direction to get here. So A is just going to be positive 1, 0, negative 1. Any questions about that? Yep. Yeah. Yeah, well, so what you're thinking of is we're isolating, and really in a way this will be easier when we start doing free body diagrams. Maybe I should have done one. But what you have to keep in mind is that we've decided to isolate the plate. And so we're trying to figure out the force. We're trying to figure out stuff about the force the cable applies to the plate. And the location where the cable applies the force to the plate is where that cable touches the plate. And so that's at the hook. Yep. So if you do a free body diagram, remember you mentally go around the boundary looking for contact, and that's the contact. Yep. Okay, so row, you just subtract those two. So 0 minus 1 is negative 1. 0 minus 0 is 0. 0 minus negative 1 is positive 1. And so to make sense of that, remember the row vector is the vector from A to P. So this orange is the row vector. So that's going, so that row vector is 1 meter in the negative x direction, and then 1 meter in the positive z direction. Okay, now the force vector. We have to deal with, question?
Yeah, so for A,
Yeah.
are we starting to measure the length starting from the origin?
For which one? For A? Yeah. These are just coordinates of points. And so, yeah, these are coordinates of points in whatever you've chosen as your coordinate system.
So that would be like the initial point.
Yeah, this is your 0, 0, 0. And you're just trying to figure out, this is the point P, this is the point A, and you're coming up with coordinates for those 2 points in the coordinate system you've defined. Okay. The majority of problems we're going to do are in 2D, and it's easier to visualize this stuff in 2D, but this is also an important skill to get. So now the force vector. How are we going to represent that force vector? We know that the magnitude of the force is 10,000, but we have to get it into vector components. How are we going to do that? Yep, exactly. So I'll call this W for wall, and I'll call this P because that's where the force is applied. And so a vector in the direction of, okay, so let me write this more clearly. So the force vector applied by the cable. So that force vector is equal to the cable tension times a unit vector u. And that cable tension is given as 10,000. So to find that unit vector u, the first thing we have to do is find a non-unit vector in the right direction. So I'll call that the u vector, and that's equal to w minus p. What are the coordinates of that point w? So let's just think of taking three legs of a journey, you know. So from the origin, we have to go in the negative x direction 1 to get there. And then we have to go in the positive y direction 1 to get there. And then we have to go in the positive z direction 1 to get there. So it's just negative 1, 1, 1. So negative 1, 1, 1. Those are the coordinates of w. Any questions about that one? And then the coordinates of p, we've already dealt with that. P is at the origin, so that's just 0, 0, 0. And so this u vector is negative 1, 1, 1. But that's not a unit vector, so now we have to divide by the magnitude of this. So the magnitude of that u vector is the square root of negative 1 squared plus 1 squared plus 1 squared, which is root 3. And so the unit vector is negative 1 over root 3, positive 1 over root 3, positive 1 over root 3. And in decimals, that is negative 5773, positive 5773, positive 5773. No, that doesn't make any sense. These are decimals. You cannot have a unit vector with components in the thousands. I skipped a step. Negative 0.5773, positive 0.5773, positive 0.57773. That makes more sense. So now if you took the square root of the sum of the squares of these, what would you get for the magnitude of that vector? 1. That has a length of 1. And now we just multiply that to get the force vector by 10,000. So the force vector is equal to 10,000 times this vector we just came up with. And this is the one that's negative 5773, positive 5773, positive 5773. And that's in newtons. We've done that kind of calculation before, but it feels a lot harder when you see it sort of cold in the middle of a separate problem about something else. But we've done that stuff before. Okay, so the force vector now for the table, remember all of that we just did to come up with this force vector, is negative 5773, positive 5773, positive 5773. And then the last step is the moment is just the cross product of rho and F. So if you take the cross product, you get negative 5773, 0, negative 5773. This one's in newtons. This one's in Newton meters.
Just one question.
Yeah.
I understand how the problem, how it's set up, but I didn't really quite get why did we use the unit vector to find
The force.
the force?
Yeah. Well, because what we were given in the problem was that the cable tension is 10,000. So we know that the magnitude of the force is 10,000. And separately, we know since it's a cable, we can figure out what the direction is. So so anytime that you have to separate the magnitude of a force vector from the direction, the way you're going to do that is by multiplying a scalar, the magnitude, times a unit vector representing that direction. So
The vector from the magnitude.
yes. So basically what we did was separate the force up into two factors, the magnitude and the direction. Yep.
How are we always supposed to round the calculation for decimal?
Oh, how many decimal places? I don't care.
So sig fig's not important?
Not to me.
Okay.
The more the better.
Okay.
Like if you really, significant figures, are a nice sort of quick and easy way to calculate what your precision is, but it's not really, there's no like, it's not really a mathematically accurate way to calculate precision. If you need to calculate precision, the way to do it is to bracket your values, figure out at every step what are your limits, you know, and go through and calculate how much you could be off in either direction. It's a way more tedious way of doing it than, so anyways, that's how you would do it if you really care about it. So that's not really an argument for not using significant figures, but but yeah, we're not going all that far. Let's just go a little less far. Any other questions about that calculation? Also, I feel better about not worrying about significant figures because I know you've had professors and you will have professors who care so much about it. Like if there weren't professors who would just freak out about what I just said, then maybe I'd be more nervous about it. But like, they freak out enough for both of us.
I'm not complaining.
Okay. All right, so that's moments. What are moments good for? And the answer is the rotational version of Newton's second law. And this is what I'm always going to abbreviate Rn2L. Says, add up all the moments about A. That's equal to the mass moment of inertia, which is a matrix in general, times the angular acceleration. And this holds for only two possible choices of A. So A has to be either fixed in the body and the coordinate system, or it has to be the center of mass of the body.
Is A still 0 at this time?
No, A is not always, A doesn't always have to be 0. Well, actually, in our last example, it wasn't either. We chose A to be away from the origin. Center of mass.
What is the squiggle on the eye?
That means it's a matrix. That's not going to matter to us, but if you look back at these notes later, that'll make sense. Okay, so this is the dynamics full form of, yes?
What other moments of A would there be? Is there going to be...
There'll be, I did this thing where we only calculated the moment due to one force, but there's also a force produced by this hinge and a force produced by this hinge.
Okay.
There's also a weight force, and every one of those forces produces a moment about A.
Okay.
And so you have to add all those up. We just did it for one. In statics, our bodies are in equilibrium. So the angular acceleration is 0. So Rn2L simplifies to the sum of the moments about A is equal to the 0 vector, And now you would think, based on the requirements from up above, you'd think, okay, well, we don't get this A can't be anything. It has to either be fixed in the body and fixed in the coordinate system or the center of mass of the body. But for these problems where we're in equilibrium, any point in the world is fixed in the body and in the coordinate system because the body isn't moving. And so this holds for any choice of A. That's a big relaxation of the rules from the real rotational equation. Okay, so there are a few things to keep in mind when you're using the rotational equation. So notice the first one is once you choose an about point, once you choose A, you have to stick with it for the whole rest of, for all the other forces on that body. So you get to choose that about point A. That's totally up to you. It can be anywhere you want. But once you choose it for the body, you have to use it for every other force on that body. Second, in 2D, the moment equation gives one useful equation. And those are the components parallel to the z-axis. So you only have non-zero z components. That's because if you think of a row vector and a f vector in the xy plane, the cross product of those two is perpendicular to the xy plane, so it has to be either in the positive or negative z direction. Okay? So only z components are going to come up in 2D. In 3D, the cross product of rho and f can be anything. So all three components of the moment vector can be non-zero, and so the moment equation gives three useful equations. Those are x, y, and z components. Any questions about anything yet?
Yes, the first one.
Yeah.
Once you choose A, have to use it for every course. What that like mean? Like, do we choose like?
Okay, so let's say if in this example, a lot of this stuff I'm saying, I think it'll, it's a little hazy now because it's sort of abstract. Once I start doing problems, it'll make more sense. But like in this example, if we would have had this cable force and also a weight force and also a force from each hinge, then we would have had to calculate moments for 1, 2, 3, 4 forces. Okay? And the about point that we use for all four of those forces have to be the same thing. So, I mean, in that example, I chose the about point A that we had to use just as an exercise. But when you're really doing physics with it, you can choose that about point A wherever you want, whatever makes it convenient. But whatever you choose, you have to keep it consistent for all four of those forces acting on the body. Any other questions? All right. So here's one unusual kind of type of moment. This is the moment of a couple. And people a lot of times just refer to that as a couple. So, like in this class, when I talk about a couple, I'll be talking about the moment produced by that couple. But really, a couple is two equal and opposite forces acting at a distance. And the surprising thing about a couple is when you have this situation, you don't just have one force vector F. You have a force vector F acting here, and then a force vector negative F acting here. The dependence on the about point drops out. And so the moment produced by a couple doesn't have anything to do with your choice of about point. So it's the same, scratch that, the moment produced by the couple is the same no matter what the about point is. Okay, so what about a moment produced by a single force? If you change the about point, does that affect the moment? Yeah, it does. You can look at the way that's calculated. Well, like for example, what if instead of, in this example, instead of choosing the about point over here at the corner, what if I'd chosen the about point at this point P where the force is applied? Then when you look at this table, well, just think of what's the row vector then going from A to P. It's 0 because they're the same, they have the same coordinates. So your row vector is 0. 0 crossed with F gives you a moment of 0. So changing the about point changes the moment produced by a force. But if you have two equal and opposite forces instead of just a single force, it doesn't, changing the about point doesn't change the moment anymore. So I want to go through that derivation. It doesn't take very long. Here's why. So let's say this is the body. And let's say that there's a force vector F acting here. I'll call that point P1. And over here, there's a force vector negative F. and I'll call this point P2. And then I'm going to choose an about point, but what we're going to see is that when we calculate the moment produced by the sum of these two forces, any reference to A drops out of the calculation. It disappears from, it's not important in the calculation. Okay, so first, the moment produced by F, I guess I'll write it like that. So what's the moment about A produced by F? Well, that's equal to the row vector. You can think of it as like row 1 crossed with F, where this is row 1. And to calculate row 1, that would be the quantity P1 minus A crossed with F. And you can distribute that through, and that's equal to P1 cross F minus A cross F. And now I'm going to calculate the moment produced by the force negative F. So this one is equal to the row 2 vector crossed with negative F. Row 2 is the quantity P2 minus A, and we're crossing that with negative F. And then distribute again, and you get negative P2 cross F plus A cross F. I pulled all the negative signs out. Those negative signs can just pull right through all the calculations. And now add these two things up. The sum of the moments about A is equal to P1 cross F minus A cross F plus A cross F minus P2 cross F. These two are equal and opposite, and those cancel out. And that was the only place that the dependence on A came into the calculation. And now you can rearrange this, and you get quantity P1 minus P2 crossed with F. So this is an expression for the moment of a couple. Okay, so what we saw was that for individual forces, the moment produced by an individual force depends on where that A is, what you choose as the about point. But for a couple, you can just think of it as a pure moment. Whatever the about point is, that moment value stays the same. So think of a couple as a pure moment. And in the table, So you have pancake, artist, row, 4, marzipan. You can forget all these. Those don't come into it at all with couples because none of this stuff matters. And then the pure moment is whatever you're given, you know, negative 300 Newton meters or whatever. Yes. Mm-hmm. An example, like if you want an idea of what a couple is, think of this is sort of an intuitive idea of a couple. You don't see this too much on bikes made now, but there used to be, on old bikes, there were screws that you had to turn that had these 2 little holes in them, and you'd insert there's a little wrench that just had 2 little pokers, a spanner tool. And you'd take this spanner tool and put one of those points in each one of those holes, and then you'd use that to turn this screw. Well, when you do that, so say that you turn this spanner tool counterclockwise, the effect is a downward force there and an upward force there that are equal and opposite. And so the effect that has is applying a pure moment to this that is independent of what you choose as the about point. Any questions about couples? Okay. So let me do a sort of a complete example. Let's say that we have a circular disc and down at the bottom, well, let's see, the radius, let's say the radius is 1 meter. Down at the bottom, we have a couple of negative 450 Newton meters. And that's how couples are going to be shown, just as a pure moment like that. And then let's say that we also have a force over here. We have an unknown force vector, F1. And over here we have a force with an unknown magnitude but a known direction. So let's say that this force makes an angle of 30 degrees with the horizontal and has a magnitude of F2. And let's say that the disk is in equilibrium. And we want to calculate what are F1 and F2. All right, well, I'm going to set up the pancake table. So pancake, artist, row, 4, marzipan. And we're just going to go through all 3 of these loads separately. Each one of them gets its own row in this table. We have to choose an about point. Normally, all things being equal, the easiest place to choose an about point is the place where you have the most unknown forces. So let's put the about point here. That's the place where we have 2 unknown force variables. And we haven't chosen an origin yet. Let's put that in the middle. Seems easier. Okay, so the first one I'm going to do is the force F1. What are the coordinates of the point where F1 is applied? -1, 0. And I'm going to do this to start in 3D so we can see how the moment comes out. Anyone have any questions about the coordinates there? And then what are the coordinates of the about point? Our about point is at the same place that that F1 is applied, so that's -1, 0, 0. Subtract, and you get a row vector of 0, which, anytime your force is applied at the about point, the row vector is going to be equal to 0. And then the force vector is F1x, F1y, 0. And take the cross product, and there's no moment. Okay, that's the first row. Then the second row, let's do F2. What are the coordinates where F2 is applied? Yeah, 1, 0, 0. The coordinates of the about point? That doesn't change. That has to be the same all the way down. Subtract, and you get +2, 0, 0. The force vector, this is F2 times cosine and sine of 150. So I'm just going to write that as F -0.866 F2, +0.5 F2, and then 0Z. The cross product is 0, 0, F2. And then the last load we have to deal with is this couple of -450 Newton meters. If it's producing a rotation, well, the symbol is showing that this negative, like the sign convention says, a positive value of the couple would be a moment in this direction. So if this is x and this is y, a moment this direction has a vector component in the positive z direction because of the right-hand rule. So when you're in 2D, a positive z component is a counterclockwise rotation. Okay, so I'm going to write this. I'm going to skip all those and write this as 0, 0, negative 450. And now we have a system of equations we can solve. Newton's second law gives two useful equations. I'm going to just take everything in this column, and that goes into the left side of Newton's second law. So F1x, F1y, the z doesn't give us anything useful. So plus negative 0.866 F2, positive 0.5 F2 is equal to zeros. And we can do the same thing with the moment column. We put that stuff into rotational Newton's second law. So the left side of the rotational Newton's second law, we only want the z component, so we have 0 plus F2 minus 450 is equal to 0. That's a system of three equations for three variables. You can solve that. You get F2 is equal to 450 newtons, and F1 is 389.7 x and negative 225 y. And those are newtons. Any questions about those?
Why you choose the rotation? This 0 plus F2, like why is F2?
I just went down the moment column and added up all the z components. Yep. Okay, that's it.